Okay, you're ready.
Okay. Okay. So thank you, Colin, for inviting me. It's really my pleasure to talk in Purdue topology seminar. So at any point, let me know if I'm not audible or less audible or I speak fast. That's kind of a real problem. So so here is an overview of what I'm going to say. Uh, First, there is a little preparation. I realized talking to other people that okay, I have to begin speaking more about what coloring is, and then the motivation is necessary because it helps you connect with work that I was actually pursuing. It was a chance discovery that led me here, and then we will talk about the main results. What does it accomplish? And then the main tools. And I will see that I may have to fast forward when it comes to that, and then a few future directions. So let me begin. So the first thing is I'm going to talk about the four-color theorem, which states that vertices of a planar graph, that is a graph that can be drawn on a plane without any edges crossing, can be colored with at most four colors, such that no two adjacent vertices get assigned the same color. So, oh, I don't know where, okay. So for example, if you look in this picture, there are four graphs, and one is planar. Number two is a famous Kt3 graph, and that is not planar. Now in number three, that is just drawn incorrectly because I can take one of these edges, the horizontal one, and pass it over this way, and it's same as the graph four, and that is planar. Okay. Then the four-color theorem is equivalent to the claim that every planar cubic, that is which is trivalent or regular, which means that every vertex has three edges meeting. Bridgeless graph is three edge colorable. So here is an example. Number one is just the graph that we just saw, and we see that okay. Suppose the leftmost vertex, if you color it by red, then the rightmost easily gets the color red because it's not in any contact with the left one. But then the one at the bottom has to get the color something different than red. So let's say it's blue. And then one on the top is connected to all the three. So it has to be even some fourth color. Number two is not a coloring, and you see why. Number three is just demonstration of that the four color theorem is equivalent to three edge coloring, and the graph you see in the middle is just a dual graph. And Tait has a proof, and you can read it on Wikipedia, but you will see that I will give a very beautiful proof of all these using after proving Tait's conjecture, or it was more like a hypothesis. Okay, so any such coloring of a trivalent graph is called Tait-Coloring or a three-edge coloring, and the number of such coloring is called the number of Tait-Colorings. Okay, so next ingredient, because we will see that my work connects these two. So let me talk about the word problem. So a group is often given in the form of a presentation with a set of generators and a set of relations. Okay, so for example, this is the well-known presentation of the permutation group, where if the index distance is more than one, then they commute. Otherwise, they satisfy a relation, and we will see today some use of it. And the word problem is a question about the decidability, which means that given two words, W and W prime, with letters in the generators, when do they represent the same element of the given group? So let's look at this example. I intentionally gave this example because that's what appears in preprint. So consider this group, which is generated by four elements, and it has a single relation, and we are not mentioning the trivial relation like A inverse or BB inverse identity. And then we claim that in this group, the word ACA equals the word B. And this can be seen by the following chain of transformations. So all I have done is that, so in general, the way we solve this problem is that we will take C, use one of the relations to write C as equivalent word, and then process it. In this case, what I have done is that I took the relation, inverted it, and inserted it in the appropriate spot, and then combined them all together. So that's what I wrote here, that replacing a letter or a word by an equivalent word is as good as inserting a relation at a suitable spot. And also note that if some word satisfy relation, then it's inverse, and a cyclic permutation also forms a relation. We'll see that it will create a pivotal role in forming a defect category of defect Bordigium. Okay, so here is motivation that what led me to this work. So, but first I want to mention that the graph Goulding approach that we saw and the actual four-color problem or theorem, it's called theorem because it's been proved using computers by Appel and Haken, as most of you have heard this. But there is modern approach to graph Goulding, and the first modern approach was taken by Penrose in 1971 paper. Ironically, it is the same paper that Lou Kaufman cited where he got his idea of Kaufman-King relation. And this idea was fully developed recently by my advisor, Scott Baldridge, and one of his students from the period from 18 to so far. The second approach comes from Kronheimer-Mrowka in his work, which uses form as introduced in the categorification of the Cooper bracket in Khovanov's work and instant-on homology. And my work, which is in archive and printed version, is going to be a bit different. It uses its central idea from spectral networks and connects graph Goulding and word problem to generalized symmetry in QFT. So it's just, we have touched it, and there are so many more things here. We will see it today. Okay, so now I'm going to take a step back and going to tell you that what led me to this work. So the Treuman-Zaslow correspondence. So here I'm talking about things that is close to SYG conjecture of mirror symmetry. And they wrote a paper in 2018 that's called Cubic Planar Graph and Legendre Surface Theory. So what they do is that they take a pair, S2 and gamma. So that means gamma is a trivalent graph. And so this time S2 has a role to play. It's not like it's planar graph, but the plane is playing some role. And so what they do, and I call that construction Treuman-Zaslow correspondence, is that they take a pair, S2 and a trivalent graph, and associate to it a Legendre surface in S5. Okay, and the key ingredient here is hyperelliptic wavefront construction modeled on gamma, and one of them can be given using stable differentials. And let's note that. And it has the property that it associates a Harvey-Lawson cone to a standard form. So maybe if I have time, I will show you a very nice, what's it called, GIF file. It's something else, but it demonstrates very nicely. So it is the same form, that the cluster of soap bubbles, but it's topological. So if you have noticed that if there are more than two soap bubbles, how do they meet? So this is associated to Plato's problem that given a volume, which surface minimizes the area. And it was done a long time ago. I don't remember whom, but for one surface, it was a sphere. Then the question was that what happens if more than two surfaces meet, or and then it was solved by Jean Taylor, and she gave the conditions. And one of them, and if you have three spheres and no more than three soap bubble can meet, and if you look at the corner, then it's pretty much look at the cone on the one skeleton of a tetrahedron. So in YouTube, there is a nice video where someone has a wire, a tetrahedron, they dip it in soap bubble and took it out, and it looked exactly how it was supposed to look. Okay, so it is the same form. So because if you consider a hollow tetrahedron, then topologically it's a sphere. With its one skeleton, it's a graph, trivalent graph. So the question is that if you take the cone over this tetrahedron, then what does it correspond in Treuman-Zaslow correspondence? And the answer is that it's going to correspond to Harvey-Lawson cone. So that's something living in R6 or C3. Now, what's more important for me or for us is that the graph Goulding appears as the following important theorem, which says that suppose you have two cubic planar graphs, which has the same number of vertices, and it has the property that the Legendre surface that it gets associated to S and S prime. They have the same genus and same classical invariant, but if they have the different chromatic polynomial, then the surfaces are not Legendre anisotropic. So something as innocent and combinatorial as graph Goulding played a very crucial role here. So it says that you can't deform one to another via Legendre anisotropy, so that each middle surface is Legendrian. Okay. So now Treuman-Zaslow construction was generalized by Caslas-Zaslow but a result analogous to form Harvey-Lawson cone correspondence was not covered. And they used the concept of N graphs, which is pretty much like, for example, so just like if you have a triangulation, then its dual is a trivalent graph. N graph, you should think that's generalization of something like that. And in this figure, for example, we see a 4 graph, and you should think that, okay, there is a trivalent graph, each labeled by some color, and there is a condition that when they should interact. Okay, so and the obvious problem was that what is the counterpart of form for a special Lagrangian constructed out of N graphs when N is greater than 2? And it is still open, and I guess that this would correspond to overlapping forms that was introduced by Khovanov in his paper on universal construction. So one way to ask this question was to look at the stable model of Treuman-Zaslow. Caslas-Zaslow was built on a spectral network and subsequent works, and one such paper called BPS graphs from spectral networks to BPS fibers suggested a wave while pointing towards a future direction. And okay, and that's the reason why I'm here at IMSC. And the idea was to consider multiple ribbon graphs and where to encode their interaction. Okay, and one crucial observation, and I will finish this section here, is that I noticed that when you consider single ribbon graph, that was already done by Treuman-Zaslow, and the hexagonal vertex. So let me go back to the previous slide. Okay, and these vertices, they are called hexagonal, where you see, for example, red and yellow meeting and red and blue meeting. And my only thing I noticed is that, okay, this is not associated to the graph, but rather to groups. And I can do that with the ordinary groups as well. So if I have a group and a presentation, I could do something like that. And then the rest is that when I consider case 4 as a special case, what do I get? Okay, so now I'm going to talk about it. But before that, there is just some background, just to remind you that a d-dimensional quantum field theory consists of the following data. So first is a d-dimensional manifold M called a spacetime. Then there is a space of fields, which are usually sections of certain principal bundle. Then there is an action functional, which is a functional from this space of fields to reals, a data of observables, and up to this, we also have in classical field theory. Now, for quantum field theory, what we have is that the expectation value of observable is given by this expression, and the GM is called partition function that is given by the famous path integral, so over summing over all the fields. Now, the scene, as most of you have heard in John Simon's case and others, that this is not well defined when d is greater than or equal to 2. And one of the remedies is to impose Frobenius theorem in the function. So partition function can be thought as it takes input as a manifold and output is a number. So that's the function, and we can try to impose Frobenius theorem. So more precisely, suppose your manifold is obtained by gluing it along a 4-dimensional 1 manifold, then locality implies that, let me quickly fast forward, that the space of field is the fiber bundle, and we can write using Frobenius theorem in this form. So like separating the integral, and you can see that it's the L2 norm or L2 inner product, where outer inner product is given on the boundary, and the inner product is given on the individual pieces. So the partition function, the moral of the story is that the partition function is given by summing all possible field configuration on glued boundary. Okay. So a d-dimensional functorial quantum field theory assigns to every d-1 dimension manifold sigma a vector space with an inner product and may have possible extra structures. And to a d-dimensional manifold with boundary, a vector space in the Hilbert space of the boundary of the manifold, which satisfies the condition that to an empty or to vacuum, it should assign complex numbers or scalars. And if manifold M is obtained by gluing along the common boundary, then the partition function should satisfy the summing over all possible field configuration. So you can take it and glue it together and you'll get a partition function. Okay. And it is called functorial because the functor G is actually a functor of symmetric monoidal categories. And just few definitions that a functorial quantum field theory is called one extended if it also assigns a structure to d-2 manifold. And it is fully extended if it assigns a structure to d-k dimensional manifold for every k greater than or equal to 0. Okay, so from here, what I'm going to mention is that, so let's now talk about the graph coloring. And suppose someone hand us a gigantic graph, like Earth is a sphere, it's a plane sitting on the Earth's surface. And what we are going to do is that we'll assign people at each vertex and ask them to color admissively. So they will do it locally, but whether this is a coloring or not can only be decided when you can do it globally or not. So the moral of the story is that the graph coloring problem is actually a local to global problem. So the picture here shows that suppose you have this graph, theta graph on a sphere, you cut it and you color it, then if a coloring doesn't match it at the boundary. So you color the top piece and I color the bottom piece, then this is a coloring if and only if it matches at the boundary. In fact, I can further dissociate. That's what you see in picture 2. And so that's the idea, is that it's a coloring if the color matches on the boundary, and it's not a coloring if it doesn't match on the boundary. So in simplest language, it's given by summing over all the possible colors that matches on the boundary. So then the natural question is that, does there exist a functorial quantum field theory whose partition function is the number of Tait-Coloring of gamma? Okay, and the answer is yes. But before that, here I want to give the reason that where I got this answer from. And so when I mentioned that, okay, I was working with K4 and then I got this picture, like something related to graph curling, then Scott pointed it out that Tait hypothesized long time ago that suppose you have a planar graph, trivalent graph, and if you assign its edges non-identity element of Klein-Four group, then there is a very nice way or elegant way to 4 vertex color the dual graph. And the way you do it is that just pick one of the color, one ABC. Let's say 1, I gave it to outer region. And as you cross an edge, multiply it by the color on that edge. So if the outer region is 1, then you see that from bottom to top, the region is colored A. Again, if you cross the red line, and red is B, by the way, then you multiply A by B and you get C. And you see that it's not a problem if you approach C from a crossing through a different path. So and my insight was only to recognize that that's exactly how defects behave. There's a paper by Karkivel on Landau impulse, and so if you have a surface with defects, and defects data is one stratum is labeled by the non-identity element of K4, then that's exactly how defects should behave. And my insight was that so some sort of defect DFT should work. I talked to Professor Ingo Rankel, and then he suggested that I should possibly consider a dynamics. I should possibly consider a theory where all the dynamics is concentrated on the edges, and that's exactly how it worked. And so building on the works of Karkivel, Kong, Rankel, Khovanov-Robert, because my work has inspired from them, we proved the main theorem, which says that there is a category of defect Bordism, so that if you consider a planar graph, then the pair S2 and gamma, it lives in its morphism set, and the functor chi CW has the property that if you evaluate on it, it's a map from C to C, so it is supposed to assign a scalar, and that scalar is precisely the number of Tait-Coloring of the gamma. Okay, so that was the first achievement. Now, second achievement of this is Tait's hypothesis. So Tait's hypothesis is an easy consequence of the following theorem, and this theorem is very one of my favorite. And it says that suppose you have a sphere graph, trivalent graph sitting on a sphere, and you colored it. Suppose it's by 3 colors successfully, and then you chop it off like the picture above and take a generic cross section. Then the product of defect has to be 1. And you can see that Tait correspondence will be, or Tait's hypothesis will be proved easily from this. And additionally, it can be easily deduced from this that a cubic planar graph with a bridge is not 3H colorable, because the moment you have a bridge, then it has to get some non-identity element, and then there is a cross section which have only single element labeled by a non-identity element, and that's not 1. So here is the reason why this theorem is stronger than the actual work of Tait. So look at figure 1. Here is a trivalent graph, and the thickened gray circle is generic cross section. Now, if it says that if this graph is 3H colorable, then the 2 edges that you see in the middle, that has to get the same color. Otherwise, the product is not going to be 1. Okay. And you can check that if you give it A and B, where product is not 1, then you will see that it will fail at some point. And same is true at number 2, where we have the generic cross section, but meeting 3 edges. And then you can see that it has to be all different color. Otherwise, the product is never going to be 1. Okay. And you can check that if you don't take A, B, and C all different, then you will you will not get a coloring. Okay. And then applying this construction to arbitrary finitely presented groups, this leads to following table where it says that, you can take a look, but that's what I mentioned. Or differently, I want to hit at the final point where it says that when two words represent the same element of the group, or the word problem equivalent to cobordism problem is when two circles with defects are cobordism. Now, there are certain works needed to be done here because I want to make sure that what kind of stratification I need. And that's why for now, it's only one way. Okay, so as I mentioned in the main theorem, that if you already have a graph that is 3-edge colored, you start taking general section, you see that product is always 1. And that makes me to hypothesize this, which connects word problem and Tait-Coloring. And here I'm using the fact that a hypothesis is a conjecture in theoretical setting. That means it's a conjecture, but there is no well-known theoretical framework to prove this. So the fact that the word problem is in the Klein-Four group is solvable because it's finite and abelian is equivalent to the Tait-Coloring of a bridge less trivalent planar graph. Okay, so that's the end of the first part. And now I'm going to move that how this is achieved. So I will pause a moment for any question.
I mean, allowing cobordism. So am I correct? The circle should have is broken up into intervals, and each of the intervals is labeled by a generator?
We will see, sir. So let me move to how it is done, and you will see the picture of defect cobordism.
Yeah.
Okay.
Thanks. Yeah.
Okay. So let me go ahead now and then talk about how does it accomplish. So let me see. Do I need to fast forward? No, I have plenty of time. Okay. So first step is to construct a symmetric monoidal category. Board to def CW. So here there is some symbol which I'm going to explain now. So first we define the category board to def T. So board 2 is the dimension. So it's the 2 defect boardism. So 2 boardism with defect, and D is the defect condition. So which is a class. So D2, D1, D0. One should think that. So D2 is the set that is available to level the 2-dimensional stratum. 1 means it's available to level the 1-dimensional stratum, 0 for the 0-dimensional stratum, and then psi 01 and psi 12 is saying that how they are interacting. And these are called the defect condition. And this is a boardism category with objects is a disjoint union of oriented marked circle marked by the elements of D. And the morphism are given by surface fit of defects, whose construction uses the fact that the class of defect conditions give rise to 2 categories. So one can check that this forms a pre-2 category, and then there is a 2 category, and thus provides a local model to define a surface with defects. So for example, it says that locally, it's a surface with defects. For example, a surface with a graph, and you level graph by something is a perfect example to keep in mind. And locally, it should look like picture 1 and 2. And then there is a condition. Oh, by the way, these are not anything new. I just made a bit more rigorous of the work of Rankel and many of his students. So it's just the new language, but the old stuff. And then there is a condition that when alpha and beta is meeting, then what should happen? So these are all you can find in the work of DKR, Kong and Rankel, and one more person. And here is an example of this. So you have left a circle. I was supposed to draw it vertical, but then there was no enough space. So this surface with defect shows a cobordism from 1 on the left to 1 on the right. Okay, and that's how in case of groups it should look like. So we will see that in case of groups, what will happen that all x1 inverse will be element of groups, and in case of for the 1-dimensional stratum, we will take trivial, but it doesn't have to be trivial. So this shows an example of a pair of pants, which is a boardism between Buddhism from circles at the left to circle at the right. Okay, and as you can see that in the morphism set, you are naturally seeing a leveled graph appearing. So that should give us the hint that what is going to happen. Okay, so the above figure shows an example, and okay, so that's something little complicated. I'm saying that, okay, so let me go back and just mention. So you see that D2 is alpha, beta, gamma, and delta, and that's what you see that this blue color, alpha, beta, and gamma, and delta, is decorations available to decorate two-dimensional stratum.
Can
Then
I
D1,
pause you?
yeah,
Sorry to interrupt.
yes.
On the previous slide,
Yeah.
the way you've drawn this this Bordism reminds me of graph planar algebras. And I was wondering if you can
in the
say
temperedly leaf sort of thing, like the
that
temperedly leaf kind of thing.
that's an example of
Okay,
such
yes,
a thing. I was just wondering if you could put your finger on like what if any precise connection there is there.
Actually, I mean, right now I don't know the answer. I know that should be in case of like when there is no vertex, then yeah, I believe that lots of things that people do with temperedly leaf or the example of like the braiding diagram, that should also come there. Oh, so by the way, like there is something called orbifold construction, and which is basically generalization of Restekin-Turev construction of that construction that they put a knot and on the invariant of three manifold. So yeah, they are related, and this version that we call is also planar defects because there's a condition and it's forcing them to plane. But yeah, I mean, I don't know much deeper, but I know that okay, there is some connection between them.
Yeah, same. I know these things are connected and I can
Okay.
articulate it in a different way, but like the picture you've drawn makes it pretty clear. Maybe someone else can chime in if they have a comment.
Yes. Okay. So then you see that D1 has this property that, okay, D1 is the set X1 to X6, and that's what you see that it's appearing here. It's leveling the one-dimensional stratum. And size 01, X1. So these codimension one stratum, they are also called domain walls. And the example we saw is also an example of wall crossing, actually. So, so for example, X1 is associated to alpha and beta, and we see that in X1 has this that, okay, it has left alpha and right beta. And that's what this picture here was showing, that this defect condition is actually forcing. So for example, if you see X here with left alpha and right beta, then whenever X appears, it has the same form, that left has to be alpha and right has to be beta. So that's why we say that, and the plan behind this is that you can take this, because eventually we want to construct a category with duals. So you flip it and glue them together so that they form a sphere. And same applies to the zero-dimensional stratum. So here it says that to you assign. So here we go back to you, and you see that I can say that how you is interacting. So I will start with X2. If arrow is towards you, I say it's positive. If arrow is away, then I can say negative. So it's X2, X5 inverse, X3, X3 inverse X1. But someone can again start at X5. And that's why there should be no ambiguity. And that's why we have to work with cyclic permutation of this. And that's why I pointed out that anytime you have a relation in word problem or in a group presentation, and you can notice that if you cyclically permute it, then it's again a relation. And that gave me the facility that I can define a defect Bordism based on groups. And by the way, this was known to physicists a long time ago. And this is an example of what they call invertible defects. Okay, so the category board to def CW is obtained from board to def D by imposing the extra condition that objects and morphisms come equipped with PL-CW decomposition. So this is called short for piecewise linear CW decomposition, and it has the property that it is more general than CW decomposition, but less general than usual convex or polyhedral decomposition. So for example, the famous CW decomposition of a sphere with single 0 cell and single 2 cell is a CW decomposition, but it's not a PL-CW decomposition. So just to give an example in mind, because what we want is that when you are gluing, then you should want that the gluing map on the boundary should be one-to-one correspondence, okay? And that is not happening in case of single 0 cell and single 2 cell. Okay, so that's the PLCW decomposition, and it was actually introduced by Alexander Grillo following Lurie's paper on extended Bordism, because it was very hard to calculate with triangulations. Okay, so now what we are going to do is that we fix our D2 state as singleton. D1 is again singleton, which I have called E for reasons we see soon, and D0 is again singleton, all singletons, and we define a category both to diff CW and Pascal D plus as the category where only defect disks of type 2. So here, let me go back. So from left to right, I'm calling this as defect disk of type 2, where you see a zero dimensional stratum meeting several one dimensional stratum. And only defect disks of type 2 are those which incident to n segments. So when you plug in n equal to 3, then you get a trivalent graph. So okay, so all I want to say that when you plug in n equal to 3 here, and that was the goal, then we should think that category that accommodates all surfaces with boundary, which has trivalent graphs embedded in it. Okay, so it accommodates all the graphs that we plan to color. So that's the base that we wanted to make. Now, next step is to use the lattice topological field theory construction to define a trivial surrounding theory by CW. So as I mentioned, Dr. Rankel's suggestion, and that's what we are going to do here. So a topological field theory with defect is a symmetric monoidal functor from the, again, both to def T to the category of vector spaces. And we are interested in the category of vector spaces with trace pairing, which restricts the target category to finite dimensional vector spaces. Lattice TFT assigns the Frobenius algebra AA to two-dimensional stratum labeled with defect condition A, AB bimodule to XX to the one stratum labeled with X, such that, so if X has the property that the left is A, right is B, then to X it assigns AB bimodule. That's what I want to say. And a bimodule intertwiner to zero-dimensional stratum. It uses the PLCW decomposition, and that's defined rather on the board 2 category with CW. Here I want to mention that even if you look at DKR paper, then the calculation goes horribly fast, and that's why you don't see a zero-dimensional stratum there. I mean, I don't know any work other than myself where you see a calculation on using zero-dimensional stratum. Okay, maybe that's why they didn't discover this property of graph curling earlier. But anyway, so a trivial surrounding theory is only defined for defect condition where D2 is singleton. So all surfaces is colored by single color, or you should say that we're actually forgetting the color. And then it assigns a field to star or the single every regions, a k vector space XX for each X belongs to D1, extended by the rule that for X inverse, so if you flip the arrow, then it should be the dual vector space. And for every U, so here I'm going to explain, it's easy to look at the figure. So suppose, as I mentioned, that it depends on the cyclic permutation. So to a vertex, you are going to assign a vector space, a vector in the home from the tensor product to K, but then it should not be dependent on the cyclic permutation. So that's why it has to be independent under the cyclic group. So one example is the map itself, which is very important for us. So this is the same ABC with K4, but right now it's just any 3 element. And then we are defining this map mu, which has the property that if all are different, this is 1, and otherwise 0. And we can check that if you cyclically permute X, Y, Z, then this map is well defined. And that's the kind of map we want. In fact, this is invariant under transpositions, so we don't have to worry about it. Okay, so for now we are done with the step 2. So let's move to step 3, and that is more crucial. So now we are going to construct a category of board to diff PK4. That's what our goal is. And we work with a specific presentation of Klein-Four Group. Okay. And the idea is that given a finitely presented group G with the presentation BG and RG, we define a set of defect conditions as follows. So you fix D2 as singleton, but D2 doesn't have to be singleton. It can be any G set, but for my work, it's singleton. And set D1 as the set of generators BG, and set D0 is in one-to-one correspondence with the words in the relation RG. So if R belongs to RG, then you set D0 level each relation by something. And the map psi1, 2 is trivial because it assigns a star to anything. But oh, sorry, my slide is cutting. It's saying that, okay, let me show that. Okay, so here is the picture. So you should think that category of defect or category is the Bordism of with defects, which morphism set is going to be surfaces with defects, which locally looks like this. So if you have G, then the first figure you see, that is kind of mimicking the relation G inverse equal to identity. It has an arrow or a direction. G square equal to 0 or identity is mimicking by you ignore the arrow. So if Vladimir has a paper on 1999 about homotopical QFT, where he actually touched this, and all these works of Rankel and others has that paper in the base. So yeah, these things was known to him. And number 3 is something that is new, and it says that suppose you have a relation like this, G1, G2 inverse equal to identity, then you construct a basic GON or defect disk labeling like this. And the fact that it doesn't depend on cyclic permutation allows you to well define it. And then we consider 4, which is like for the commutator, we are like passing it nicely. So like in virtual knot theory and others, we should think at it as a vertex, but you can see it in my paper that it has a property that if you vertically compose, then that's idempotent. So it's identity. So that's a special kind of vertex. And the way we chose it, because to match with the earlier theory of n-graphs, I mean, I forgot to mention, but there in a spectral networks, what happens that there are disks level by permutation groups, and anytime you have things commuting, then they can pass with each other. And that actually follows from the root system of Lie algebra. Okay, so now we consider a specific presentation of Klein-Four Group, and then we have this defect disk. And as you can yourself see that, okay, from looking, it looks like that we have vertices, and every time you have a vertex, there is 3 colors meeting. And then what will happen is that the morphism set of this category contains in it all pairs for any surface sigma and the Tait-Coloring trivalent graph gamma prime. Okay, I want to take a step back to show something, that this construction is not as new as it seems. So look at picture 3, and consider the dual graph. If you consider the dual graph, then you see that what will happen is that you will get a disk. For vertex, you will replace by disk, and then edges will be traversed by the relations of the group. So, and we know a construction where we have a category where you attach relations of the, attach disk as they're following the relations of the group. So related to KG1. So it's some way related, but it's in dual words. So I don't know how, lots of things happen in this work that are developed, but, there is scope of further development. So just to connect that, this is, at some point, it's merging with KG1 if you consider the, not KG1, but some stage of KG1 if you consider the dual graph. Okay. So the morphism set of this category contains in it all pairs sigma gamma hat for any surface, possibly with bounded sigma and the Tait-colored trivalent graph gamma bar. So this surface has this property that it accommodates all the graphs, trivalent graphs, sitting in any surface which is already 3H colored. So this is a good point to mention that in all the 3 approach we talked, we are not talking about abstract graphs. So for the Penrose approach or Bullrich and other approach, they use ribbon graphs. For Kronheimer-Mrowka and Khovanov others, they use waves. And I'm using something very different. So kind of a category, which is coming from a 2 category, and it has the property that it contains all pairs, sigma and gamma bar. So it accommodates. So we'll see that it should somehow lead to some sort of categorification of universal bundles. Okay. So then once you have that category, which has the property, so now we saw that we have 2 categories. One accommodates all the graphs that we want to 3H color, and then one category that accommodates all the graph that is 3H colored. And then the idea is that, okay, then we can lift, once we have such a category that accommodates all 3H colored graph, then we can try to redefine graph coloring in terms of lifts. And here is the failed attempt. So now define the coloring of a trivalent planar graph in terms of lift to the category board to diff. And theorem 5.13, which we met earlier, says this may not always be possible. So recall this theorem, which says that anytime you have a graph sitting in a plane, and you take a generic cross section, the product is 1. And that says that, okay, anytime you have a bridge, like a dumbbell graph, which I forgot to include in the picture, you can't 3H color it. So that's the obstruction that it gives. Is that the only obstruction? That will prove the four-color theorem. Okay. So then the correct step is that define this lift only locally. And it is a coloring of a given trivalent graph precisely when all these local lifts are glued together to produce a global lift. So I should have, I forgot to mention that picture, but I don't know if in the picture with Tait correspondence, if you saw on the right, there was seed sort of thing going on. And that seed sort of thing has a property that, okay, let me see if I can go back quickly. How much time do I have? Yeah, I do have plenty of time. So, okay, so let me see. Okay, so here you see that, so in the base there is a graph. I'm taking a disk, basically a neighborhood, and you have a 3 colors, which is all possible colors. Here I want to highlight that if you take any point, any neighborhood away from the vertex, there are only 3 sections. Something goes wrong at the vertex. Like it's not right to call it branch covering, but yeah, the number of seeds of the covering changes. So analogous to branch covering. The reason I pointed it out is because that has something to do. I discovered this thing when working with spectral networks, and that's how spectral networks is defined using branch cover. So I don't know if there is any connection, but that's what I was pointing out, that you lift to the older, the newer category. Okay, so let me come back. And that lift was local. So, okay. Okay, so define this lift only locally, and it is a coloring of a given trivalent graph precisely when all these local lifts are glued together to produce a global lift. As we just saw in that picture, that in the intersection, lots of these lifts were not well defined. So thus we distinguish a coloring process, which is just the name I gave for a local section, from a coloring, which is a global section. So a trivalent planar graph is 3H colorable if it admits a global section. Okay. In general, not all coloring process leads to coloring. And if the graph has a bridge, then no coloring process would lead to coloring. Okay. So, I mean, is that the only one? And that's basically a statement of four-color theorem. Okay. So now I want to talk about some future direction. And the first one is that, so I was only talking about, or my theorem is only working for the planar trivalent graphs. Question is that, what if your trivalent graph is sitting inside other genus G surface? And I have done it already using a variation of universal construction, but it's not there on definite yet. Then the second is that reformulate in the language of infinity n category and develop higher obstruction theory. The reason I pointed it out is that, so what I'm saying is that that category, both to diff PK4, has that property that if you have any graph and a coloring, then it has a representative in it. Now, this kind of thing is something that should remind you of universal bundles. And that's why I'm asking that, can we talk about higher obstruction theory? And then dig deeper into the connection of Tait's hypothesis. Now, here is something interesting. So consider a graph. So take a torus, consider the theta graph in a way that one of the, so in the theta graph, or if your graph is already 3H colored, then it has the property that if you take the union of two colors, gamma AB or gamma BC, it's a Jordan curve. And if you take this curve as in a way so that your graph sitting embedded in a way so that these curves are not trivial in the first homology group, then you see that the Tait-Coloring will fail. And that is very close to spectral networks. So that's why I said that, and then more on categorical symmetry, because I just touched the defect DFT, so particularly with the ideas developed by Freed, Moore, and Tellman. And here I didn't mention the goal, actually what the goal is, but I want to say it. So the Kronheimer-Mrowka, they constructed a functor for waves called J-sharp. And they conjectured that there is a combinatorial analog of this functor, usually called J-hat, which should do the same job. And J-sharp has the property that it is if and only if. It says that if it is the breeze, then it is 0, and if it is not, then it's not. And they suggested that there is a combinatorial analog, and then Khovanov and Robert constructed that, and my work is influenced by their work quite a lot. And it was only recently debunked by David Boozer, which proved that they are not same. And that's why obvious question I'm asking is that, is there any connection between J-sharp and chi-CW? But the big problem is that it's defined, they both are defined on a very different sort of gadgets. So that's what big question is, that how J-sharp is connected to chi-CW. And then the main lemma which I used, but the main idea was to use the factorization algebra, because I'm talking about that C picture that we show, and prove that those categories are equivalent. So then that's what I'm working on these days. And then explore the connection between N deformations. So yeah, that's there's another hypothesis, is that when we work with other groups, like, and we need higher N, and then this is a hypothesis because we don't know how the spectral network looks in higher dimension. So that would tell us more about Andrew-Curtis conjecture, if we can talk about N deformations or in this language. So I don't know how did I do. It was a bit sleep time here, so I don't know. Maybe I was speaking too fast, but yeah. So that's where I want to end, and with one of my favorite quote. Okay.
Thank you.
Thank you.